Hello everyone and welcome to this last lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. After this we will have a tutorial about neural networks which will form the next two videos. So this is in principle the last theory lecture. In today's lecture we will continue from where we stopped last time, which is where when we had delved into the concept of generative AI via the use of generative adversarial networks as well as variational autoencoders. Whereas we finished the topic of GANs last time, we were not able to take up the topic of variational autoencoders. So that will be the focus of this particular lecture. So let us go ahead and get started with the topic of variational autoencoders. So we already discussed the concept of an autoencoder very briefly when we were talking about neural networks, and we know that an autoencoder essentially maps you from the feature space to a latent space and then back to the feature space, right. So that is a vanilla autoencoder, but that is not very useful because it is unable to learn the distribution of data. We want the VAE to learn the distribution of data. So that is where the variational part of it, wherein you teach it to learn the distribution, comes into the picture. Okay. So a vanilla autoencoder which simply maps data from the feature space to latent space and back is not very useful for generative purposes, right, as it does not learn the distribution of data. Right. So how do we get a neural network, right, or two neural networks, the encoder and the decoder, to learn the distribution of data within a Bayesian framework? So that is what we will learn under variational autoencoders. Okay. So what a VAE does, it learns the conditional distributions underlying the feature space and typically we denote a point in the feature space as x and the latent space wherein we denote a point as z. So a VAE learns the conditional distributions underlying the feature space and the latent space and allows the application of a Bayesian framework. Okay. So essentially if you wanted to write the Bayesian probabilities, so if you have a data point xi in your feature space, then probability of the point xi times the conditional probability of z, the latent space variable given xi, will be equal to the probability of z times the probability of xi given z. Okay. So this is essentially a statement of the Bayes theorem, and you can recollect all the terms that appear here, right. If you recall this PZ, right, that is what we will call the prior distribution, and typically like we had done in the case of generative adversarial networks, the points in the latent space, right, you will just assume them to follow a normal distribution with mean 0 and the identity matrix as the covariance matrix, because it will have multiple features in the latent space, right. So that is the prior distribution. Then of course you have the likelihood and the posterior. So this probability of xi given z, that is the likelihood, and then probability of z given xi, that is the posterior. And finally this p of xi, that is basically the evidence. Right. Now if you remember, in an autoencoder there is an encoder and then there is a decoder. So the encoder takes you from the feature space to the latent space, and the decoder brings you back from the latent space to the feature space. So how are the encoder and the decoder entering the picture here, right. So this likelihood, this is what is accomplished by the decoder, okay. It tells you the probability of xi being the point in the feature space given z is the point in the latent space, right. So it takes you from the latent space to the feature space, and that is why the likelihood is essentially the decoder, right. Now this posterior distribution, probability of z given xi, that is very difficult to get because we do not know what it is. So it is approximated by the encoder, right. So given xi, you need to go to the latent space. So given a point in the feature space xi, you want to go to the point z in the feature space. So this is approximated by the encoder by denoted by q of z given xi, right. Because this is an approximation, we will not call it p of z given xi, it will be denoted as q of z given xi, okay. So now you know where the encoder and the decoder come into the picture in a Bayesian framework for a variational autoencoder, right. So now what happens in practice? So in practice, both the encoder and the decoder output the properties of a probability distribution. Okay, and by properties of the probability distribution, it could just be the mean and the variance of a normal distribution, or it could be the probability of success in a Bernoulli distribution involved in classification, and so on and so forth. Okay, so let us write this down more formally. So essentially an encoder denoted as phi will output q z, it will model your probability q of z given xi as a normal distribution, right, over z with the mean and the variance depending on the data point xi under consideration. And again we will assume the covariance matrix to be a diagonal matrix, right. There is only variances on the diagonal and then the covariances are 0. Okay. So your encoder will output the properties of a probability distribution, and these properties are essentially the mean and the standard deviations or the variances. Okay. So that is what your encoder will tell you, and then what the decoder will do, and the decoder denoted as theta will essentially give you the probability distribution of x given z, and then you can sample from that distribution. Now depending on the type of variable that you want to generate, whether it is a real valued variable or it is binary data that you want to generate or a categorical data, you may have different types of outputs, right. So if you want to generate real valued data, and this could be true if you want to generate an image, right, then you want to generate the pixel probabilities, right. So that will not fall under this categories, right. So if you want to generate an image with pixel probabilities, then you will have to go to the binary part, but if you want to generate a real value data, that is where this will come into the picture. So this is based on Gaussian likelihood, and here you will, the decoder will output again the mean and the standard deviation mu and sigma, right, and in practice the sigma is many times set to 1. So then your decoder will simply output your mu theta, and then you must sample from this distribution. If you know the mu, you can sample from the normal distribution, right, that we already discussed. Sampling from various distributions is an important part of probability and statistics. If you want to generate binary data, on the other hand, this will be based on the Bernoulli distribution or the Bernoulli likelihood, and then the decoder will simply output the probabilities p hat, right, as a function of z. So these are the probability of success. And finally, if you want to generate categorical data, right, and this is where if you want to generate words, right, then you want the probabilities of each category or each word. So text generation will fall under this categories. So here you will have to predict the class probabilities, right, and it will have to output the probability of every class k, okay, and this, the probabilities can be obtained with a softmax function, okay. And finally, to get x, we can sample, pick a random number following this distribution. If you want less creativity in the model, you can just output the mean of the model, that is a possibility, but then the creativity of the model, right, wherein you get new ideas, new candidates, that is lost, okay. So now how do we set up all this in a Bayesian framework, right. So in the Bayesian framework, we want to maximize evidence, right. So we want to maximize the probability of the point being xi, right, given we have the latent space features z, right. So we want to maximize the evidence, that is p of x, right, and we already saw using Bayes theorem, that is essentially p of z times p of x given z divided by p of z given x. And you also remember that the numerator is modeled by the decoder and the denominator is approximated by the encoder, right. So p of x given z, that is essentially your decoder, and then this is basically approximated by an encoder for q of z given x, okay, since the posterior is difficult to get, okay. So how do we set up this maximization problem, particularly because we do not know this P of z given x. So that is the crux of the problem, right. So we start with P of x as basically the integral over all possible values of z. So that is probability of x given z times probability of z dz. Okay. So this is if you were to integrate out over the latent space, right, this is the probability of x, right. Now we want to, we do not know this probability of x given z, right. So we want to represent that as the decoder, but we also want to involve the encoder in the process. So what we will do is we will multiply and divide by q of z given x here, and this part will remain as is. If you do that, you can interpret this whole integral as the expectation value over the distribution that is represented as q of z given x, right. So this concept of expectation was something that we covered very early on in the course, so that will be used here. Why we are multiplying and dividing by the encoder is that it allows us to invoke Bayes theorem inside this integral. So this becomes the expectation value over the distribution q of z given x of P of x given z, which is basically done by the decoder, times the P of z, which we will model as a Gaussian, and then finally you have introduced the decoder as well. Okay. So essentially log of P of x, right, is log of the expectation value over q of z given x of the probability of x given z, right, the feature space point given the latent space point times the probability of the latent space point divided by the approximation for the probability of the latent space point given the real space point. Okay. Now the log of the expectation can actually be related to the expectation of the log, and that is what we will do here. So we will apply what is known as Jensen's inequality. Okay. And this kind of an inequality can be written for both concave and convex functions. Now log is a concave function. So for concave functions, your function applied to the expectation is greater than or equal to expectation applied to the function. Okay. And you can see that in a simple plot here. If you take a 1D plot of f versus y, right, and I am modeling f as a log here. So the log plot looks something like this, right. It goes to minus infinity at 0 and then it keeps on increasing, right. Now if you pick 2 points here, let us say this point here and this point here, and then connect them by a straight line. Now this point is the average of those 2 points. So the so if you read out this value and then compare it with this value, right, the higher value, right, that is basically the first term here, right. So that is f of Ey, right. So this you can interpret as the average or the expectation value. So f of E given y, that is the higher term here, that is greater than expectation of f of y, right. So because you are taking here by drawing this straight line the average of the two endpoints, right. So this is true for concave functions, and log of course is a concave function. Essentially what we are stating here is that the average of the function is smaller than the function of the average. Okay, so that very simple principle is what we are applying here. So once you do that, if you applied Jensen's inequality, and I already told you that log is a concave function, so log of this expectation must be greater than equal to the expectation of the log of this, right. So let us write that. So log of p of x, we just showed that this is equal to log of the expectation over the distribution q z given x of p of x given z times p of z divided by q of z given x. This by Jensen's inequality is greater than equal to the expectation of the log. Okay. So this is where we have reached. Okay. So we have just proven that log of p of x, so log of the evidence, that is greater than equal to the expected value over q of z given x of log of p x given z times p of z divided by q of z given x. This term on the right, because the left involves the evidence p of x, right. So p of x, if you remember, that is the evidence in Bayes theorem. This whole term on the right hand side, that is a lower bound for the log of the evidence. So this is called the evidence lower bound, ELBO. Okay. So what we can do is we have to maximize log of p of x, right, or maximize p of x. So instead you can just maximize the evidence lower bound, ELBO. Okay. In fact, one can show the exact relationship between p of x and the evidence lower bound, that can also be done. Okay. But we will not be doing that here due to the lack of time, but like I said, here we have just derived an inequality. It is actually possible to derive an equality that links p of x with the evidence lower bound, and that will involve the Kullback-Leibler divergence, which we encountered earlier in the course. We will again encounter slightly later, but that is something which we can which you can take up separately. The crux of the matter is that we had to maximize the evidence, which was p of x. So instead we will maximize the log of p of x. So maximization of p of x is same as the maximization of the log of p of x, because log is a monotonically increasing function, and because p of x has a lower bound, you can just maximize the evidence lower bound. Okay. So that is how a variational autoencoder operates, right. Instead of maximizing the evidence, it maximizes the evidence lower bound. Okay. So you are maximizing now E over q of z given x of this particular term, log of p x given z times log times p of x given z times p of z divided by q of z given x, and using the concept of a log, right, and the linear property of an expectation, this can be split into two different terms. The first term is the log of p of x given z, that is the numerator here, plus you will have also another expectation of over q z given x of the remaining term inside the log, that is essentially p of z divided by q of z given x. Okay. Now if you remember, this expectation is just a shorthand for writing an integral, and the integral is over q of z given x times log of p given z divided by q of z given x times dz. Okay. The other thing you can do here is this, I am only writing this for the second term, you can take minus outside the log. So, this becomes minus of qz given x times log of qz given x divided by pz dc. Okay. Now, if you recall, right, and it may have been a while, so you will have to look over your notes, this is known as the Kullback-Leibler KL divergence between the distributions qz x and pz. DKL between qzx and pz, right. So, without the minus, this is the Kullback-Leibler divergence. So, what we have shown now is that the objective function to maximize the evidence that has two terms. So, the first term is expectation over q z given x of log of p x given z, and the second term we have managed to show that it is minus of the KL divergence between the distributions q of z given x and p of z. If you remember, we had encountered the KL distribution in the context of nonlinear dimensionality reduction, in which we were trying to ensure the similarity between the distribution in the original feature space and the dimensionality reduced feature space. So, in that context, in nonlinear dimensionality reduction we had encountered the KL divergence, but it is showing up here in variational autoencoders as well. Okay. So, this is the objective function here, and as you know by now, the maximization of function is the minimization of the negative of that function. So, this can be written as the minimization of minus the expectation over qz given x of the log of p x given z plus the KL divergence between q of z given x and p of z. Okay. Now, this loss function L, right. So, we can denote this as minimization over the loss function L, and this loss function has two terms. The first term only involves the decoder, right, involves your decoder p x given z, right, because you are going from the latent space to the feature space, and then this term involves the encoder, because you are going from the feature space to the latent space. Okay. So, the first term is called the reconstruction loss, because you are reconstructing the feature space from the latent space, and the second term is interpreted as a regularization of the latent space. The fact that you are making these distributions more similar, if you remember, the DKL KL divergence is a non-negative quantity. So, the lowest possible value is 0, and that is when these two distributions q of z given x and pz are identical, right. So, what we are trying to do is we are trying to minimize the difference between these two distributions to improve the generalizability of the model, and that is why this term is interpreted as a regularization of the latent space. Okay. So, what we have managed to show here is that a variational autoencoder which involves an encoder and a decoder involves two terms in the loss function. One term which is the reconstruction loss solely focused on the decoder, and the another term focused on the regularization which solely involves the encoder. Okay, now we just quickly will tell how these two terms can be written for a Gaussian likelihood. So if you look at the reconstruction loss, right, for a Gaussian likelihood scenario, which is what we discussed for a continuous variable. When you want to generate a continuous variable, then your minus of the expectation over qz given x of log of p x given z, you can show that this is basically sum over all the data points, the squared norm difference between the actual point and the reconstructed point. Okay. So xi is representing the original data point, right, in your training set, and this is the reconstructed after sampling, right, from the posterior distribution. The data that you get, that's the reconstructed data. So the first term, reconstruction loss, is essentially this term here averaged over all the data points. And then if you look at the regularization loss, right, this essentially is the KL divergence between the distributions q of z given x and p of z, and this can be proved to be 1 over 2n sum over all the data points and sum over all the features in the latent space. So j going from 1 to d of mu ij squared plus sigma ij squared minus log of sigma ij squared minus 1. Okay, and I'll tell you what these terms mean. So d here, like I mentioned, that's the dimension of the latent space, right. That's again a hyperparameter that you can consider while training the variational autoencoder. And then these mu's, right, these were, if you recall, the outputs of the encoder, right, which are the mean and variance of the posterior distribution. Okay. So now we are almost at the end. We know how the loss function looks like, why it looks the way it is, right, why there is a reconstruction loss involving the decoder and a regularization loss involving the encoder, and we also know based on the data points how to compute the reconstruction loss and the regularization loss based on the latent space, right. So this is the conceptual framework, but of course if you go into Python you can write all of this, right, in a few lines of code or many lines of code, and you will be able to implement it. Okay. Now one last thing is remaining: how can you generate a new data point? So just like we did in the case of a GAN, to generate a new data point, right, we sample the latent space with the prior. So sample z from the prior, and if you remember, the prior is simply a normal distribution with mean 0 and covariance matrix equal to an identity matrix. The second step is you essentially feed the sample z, the z that you obtained, to the decoder and sample x from the resulting distribution. You know that the decoder will give you the properties of a distribution, and that distribution you can choose to be a normal distribution if you want to predict continuous valued output, or it could be a Bernoulli distribution if you want to predict a classification or a binary output, right. So here you just sample from this distribution and you get the new data point x, that x hat that you are after. Okay. So this brings me to the end of the last lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. Today we have discussed in a lot of detail how a variational autoencoder works, though we have considered only the conceptual framework and less of the mathematics. I hope it provides you with the necessary ammunition that you need to go ahead and carry out research and develop models that involve not only VAEs and GANs but also other types of generative models that we did not have the time to cover in this course. Thank you for joining. I hope you learned something new today. The only remaining part of this course are some tutorials on neural networks, and that is what we will be taking over the next 2 videos. I look forward to seeing you next time.